Okay, so I guess it's a great pleasure to have Dr. Pedram Roushan from Google AI Santa Barbara today with us. So Pedram got his PhD in 2011 from Princeton University. Back then, he was interested in scanning tunneling microscopy of topological materials, mainly topological insulators. So he did actually phenomenal work with Ali Yazdani that actually got a lot of attention. And I was kind of young at that point, so I was following the work. Then after that, I guess he was very interested in quantum computing. And then he joined the lab of John Martinez in UC Santa Barbara as a postdoctoral fellow. And he was there for 3 years until 2014, when basically most of the lab moved to Google quantum hardware. And where they basically started making the superconducting qubits into actual processors that can be used for more realistic applications, I guess. And I guess, as you know, in 2019, there was this famous Google paper that the claim is that they can perform computation that is basically faster than any supercomputer or classical computer. And I guess the last year, it was basically a plethora of new discoveries in time crystals and a lot of other things that you can, I guess, now start simulating with these processors. So Pedram has been at the forefront of all of this. I also want to personally thank him because he has given a lot of lectures at NYU for our quantum classes, and all the students loved it. Thank you, Pedram.
Thanks, Javad, for the invitation, and thanks everybody for being here. Hopefully, I make this hour useful to all of you. I'm a member of the Google Quantum AI team, and this is one of our last pre-pandemic pictures taken the rooftop of Google building in Los Angeles. And this is the core of the people who participate or contributed to the quantum supremacy paper. After that, we keep hiring and expanding. The current size of the team, which I don't have a picture of, is about twice the size. And the work that I'm about to present to you is mainly the work that this group of people have put together, the infrastructure that they are putting together. And we are expanding, still hiring in all frontiers, and let us know if you're interested. As Javad mentioned, a little more than 2 years ago, we put this manuscript out, which communicate the technological advancements and infrastructure that we put together since a decade before that. And this manuscript really summarizes that work. But as some of you, well, maybe I just give a quick refresher of what the work is, and then I think become obvious, the shortcoming of it, in a sense, become obvious at the same time. In this work, we had a 2D grid of 53 qubits, and we talk about their fidelity in great lengths of what we are doing with them, and how we are characterizing their performance in terms of fidelity. And remember, the fidelity notion is extremely important, because if these fidelities were 2 times or 3 times worse than what you see in here on top right, this computation could have been simulated very, very easily in a classical computer. So there's not a big, there would be no advantage using quantum processor. The task, the question we pose was that if you have a given initial state and a sequence of gates, what is the evolution of that wave function? Can we sample from that wave function more reliably or man faster than a classical computer? So the boxes and the symbols represent 2-qubit and single qubit operations that you apply them in several cycles. And then at the end, you measure all the qubits. So in this case, you get a bit string, which is 53 digits long. And you claim that you can do this. And these are really coming from wave function evolution. And we are sampling the wave function better than any classical computer. So that's a claim of the manuscript. And there is a work by Vazirani and his team that's showing that this computation is in fact hard. because the gate sequence chosen are random quantum circuits. But you can see, although it's a well-defined and well-posed question, but it's rather arbitrary question. And as also Javad mentioned, we are interested to move on to see what can we do that we are making a larger crowd of people interested in this. And the problem are not so intentionally defined that we know we have an advantage over, but is the problem that people are really interested in knowing what on the outcome of it. So, and here is a very crude approximation or a sketch of what interesting problems are and what it takes to outperform a classical computation. And no surprise, the lower left is where the quantum supremacy is, the least number of qubits and the most tolerable case to quantum errors, general error of a gate, both systematic and decohering error. And we anticipate that questions related to spin dynamics, non-equilibrium physics, is really the next thing that we can probably have something sensible to say. And if you could do much more twice more qubits and much better gates, note that the vertical axis is logarithmic, then you can have a chance of saying something about problems of interest in the domain of chemistry and fermionic simulation and dynamics of electrons and whatnot, but they need far better gates. Alternatively, you cannot make the qubits much better in terms of gate fidelity, and you can make a very many number of them and put them together and hope to achieve a certain fault tolerance by making big logical qubits composed of many faulty physical qubits. And that is not the subject of this talk, this part. The subject of this talk is our effort on going up this and trying to make more higher gate fidelity. And but you'll note that it doesn't take much more qubits to do. And you note that our condensed matter friends and people in non-equilibrium dynamic physicists are usually not as good as in numerics than chemists. So they are providing the lowest hanging fruit in here. By the way, I'm happy to be interrupted any minute to answer questions so I can adjust the pace of the talk, but I don't see any chat or anything. So please just open your microphone and ask me directly. And is this effort is the underlying physics and the underlying effort in the lab, which results in this manuscript that I was showing on the first slide. Essentially, to outperform a classical computer, you either need better algorithm, you need better gates, or you need better measurement. And we are pushing in all these frontiers, and we are making incremental progress. And you can see it through these manuscripts, although may not be super visible from the first read of a manuscript, but that's the physics that we are trying to advance. Simpler algorithms which are doing more physics, more friendly to our platform, better gates, and better measurements is really the underlying of all these things, all these works that you are seeing together. Okay, just to be sure that you know what superconducting qubits are, I picked this picture, which is done by Charles Neal. Is a chip made by Charles Neal when he was a grad student, so I can share this picture. It's rather old, but the physics and the way we lay out qubits is currently more or less the same. What you see here is pattern of aluminum lithography, lithographically made on top of inert substrate. This and the colors you see are just painted in Photoshop, so you know which element is what. The long straps of aluminum are the capacitance of the qubits, and what you have not be able to see easily is this Josephson junction, so they form a nonlinear resonator here. And this two squares you see here is another way of making qubits, which is much farther further up in frequency, maybe about 15 gigahertz or so. And these are virtual hopping through them act as provide the coupling between the qubits. So these, we call them couplers, essentially is another qubit at a different frequency. And you see a bunch of wiring coming from below, and these would control the states of the qubits and the state of the on and off of the coupler. And you see some meandering line on top. This is a linear resonator. That's a flute. That's a λ/4 resonator, which this frequency, resonance frequency, sensitively depend on occupancy or lack of occupancy of a qubit. If this qubit is in 0, this qubit, let's say, for instance, reads 8 gigahertz. If it's at 1, then the resonator resonance frequency would shift to, let's say, 7.997 gigahertz. So it's this 3 megahertz shift is sufficient to know the state of the qubit coupled to it. You see 2 lines up here, signal comes and goes, and these resonators are slightly different from each other in terms of resonance frequency, so you know which one is associated with what qubits, and so you can read the state of the qubits all at the same time in one shot. So you get a bit strings, which is in this case is 9 digits long, and from that you can repeat that for a million times in a second, and you can really make expectation values and whatnot. If that was too much hardware and you are into Hamiltonians, I can tell you that if you excite a couple of these qubits and you let the microwave photons to go across this chain freely, it would be described by the Bose-Hubbard Hamiltonian. You can occupy a given site by a bunch of microwave photons, and they would hop around because of the couplers, and the nonlinearity of the qubits appears as an attractive Hubbard U term in the Hamiltonian. And we do have several works which directly work with this, but usually we tailor these terms and turn on and off the couplings and whatnot to synthesize a gate with them. The first manuscript that I like to present to you guys is about Toric code and appeared in Science a few months ago. And it's done in collaboration with Frank Polman and Michael Knapp from TU Munich, and Christina Knapp, which was at Caltech at the time. And on the left, you see the Googlers who contributed substantially to this work and play a major role in this project. Of course, this also means that every member of the quantum team helped with the infrastructure that led to this work. So here's the idea. We're trying to synthesize or realize the states, or ground state particularly, of this Hamiltonian, which been written by Kitaev more than 20 years ago, about 20 years ago. And we know its ground state have topological property. Also, there are 2 ways of doing it. One is, as you guys all know, in making topological state, is to have a condensed matter system, which is ground state, have this property, is realization of this Hamiltonian, or a spin liquid Hamiltonian. And you guys know, as condensed matter theorists and experimentalists, how challenging it is. Another way of dealing with this Hamiltonian is just to synthesize the state by sequence of gates. But the topological property implies that there's a long-range entanglement. So you really need a good sequence of gates that is effective in arriving at the ground state of the system, in synthesizing the ground state of the system. And in that, you're fighting the coherence in the system. So you have to really balance this too. So the Hamiltonian is telling you that if you have a grid of qubits, here represented by these dots, anytime you see them forming a plaquette, you would write XXXX for that plaquette. And every time you see they are forming a star or a vertex, you would write ZZZZ. So this is how the terms of the Hamiltonian are coming about. And then Kitaev really showed that beautifully, that the depending on the boundary condition, depending on how you terminate this, he put it on torus, but also you can realize you depending how you don't make it on torus and you open the boundary condition, you can manipulate the degeneracy of the ground state of this Hamiltonian. When you put it all together, and in a minute I explain to you how we got there. This is what we see. This is a grid of 31 qubits, and we can measure the X parity. This is the product of 4 X operators, and we are showing them here. This every time I say you see them forming a square, you measure X parity. There's a term in the Hamiltonian which is this, and you can measure it, which is meant to be nominally to be 1. And every time you see a star, maybe it's harder to see in here, you measure the ZZ between them, and here is the answer. So I'm about to tell you how we got there, so this is the realization of the ground state of this Hamiltonian. Full tomography would prove to you that we have done it correctly, but at least here I'm providing some evidence that these limited sets of measurements shows result consistent with realizing this state. Well, there are 2 ways of making and realizing the ground state of this system. Either you're smart and you come with a sequence, or you're not smart and then you find a collaborator who's smart and they tell you what to do. So we had to choose the latter option. And Frank Polman and his team told us that with a sequence of gates, which is in fact linear in one dimension of the system, so it's you have n qubits, this gate sequence is square root of n in the number of layers that you have to do. So it's quite effective. You can arrive at the ground state of this Hamiltonian. The insight, it comes from maybe rather well-known fact that the ground state of this system is superposition of all possible plaque configurations. If you know that fact, then you can turn this knowledge into a gate sequence, which you start with all the qubits on 0. That's trivially achieved by just waiting for all the coherence do its job and qubits lose their photons. And then you apply a Hadamard to top of each plaquette. That puts all the qubits in equator. And with a sequence, properly ordered sequence of entangling gates, in this case being C0, you can arrive at this ground state, which I'm showing its limited property, mainly its value of its stabilizers. So here we are claiming that we have realized the ground state of this Hamiltonian without having the Hamiltonian. We do not have the Hamiltonian of the system, but we could synthesize the state. A very nice property of this eigenstate that we have realized being the ground state is its entanglement entropy. And I want to show you our measurement of topological entanglement entropy, which we have done for the very first time. The beautiful property of this Hamiltonian in its ground state is that if you want to know the entanglement entropy of any subset of qubits which is surrounding, you can draw a line around that subset, and you can count how many stabilizers, X stabilizers in this case, is cut. And then you just count that number, -1, and you put log of 2 here to make peace between condensed matter people and quantum information people, which always fight over this log of 2, meaning the degree of the freedom of a single qubit. So you can see that we just know by simple counting, if you have 4 qubits like here, what should be this entanglement entropy, and so on and so forth. So entanglement entropy of each subset has 2 contributions. One is coming from its edge effects, its surrounding. Another is this universal topological entanglement entropy of the system. If you manage to put these subsets next to each other with these configurations, then you can remove the edge effects and you would be left with a pure number, which is the topological entanglement entropy. You will start with SA, entanglement entropy of subsets of 3 qubits in here, for instance. You get contribution from all these edges. But when you subtract AB, you're removing the contribution of this edge. And then you have removed too many edge effects that you have to add the whole thing back again. So if you go through and look carefully at these summation and subtraction, it remove all the possible edge effects. And you would be left with a pure number, which is the topological entanglement entropy of your system. You should get the same number regardless of these subsystem sizes that you are dividing and you're getting at. So let me start with the top row. And we are focusing on this 2 by 2 size. So here we are showing the histogram of entanglement entropy of subsystems of 1 qubit. And given the rule I mentioned, the histogram is centered around 1. So its entanglement entropy is just 1. And you do subsystem of 2 qubits, you get 2. You do 3, you get 3. And 4 is the first time that you can define the notion of interior, and the entanglement entropy of subsystem of 4 qubits actually depend on its geometry. You can see that here you have 4 qubits, its entanglement entropy is different than you have 4 qubits, which are closing on each other. And 5 and 6 and 7 gets harder and harder. You can get different values. But you can imagine I have different configuration. I can choose in my 31 subsets of qubits. So you have a histogram. You can measure entanglement entropy of subset of 2 qubits in many different places and many different configurations. And that's a histogram of them. So you can play this game and go all the way to this 3 by 3. And for the first time, we could approximate this entanglement entropy. Well, the way we technically or typically do it, we just get the full density matrix. We measure its purity from there, meaning that we get the trace of rho squared, and then log of it is just Rene second Rene entropy. But this would take a month if you want to do it for 9 qubits. That's just this data point. So for just this 3 by 3, we have to get again get more clever or find a clever person. Again, we did the latter. So this is the work of Peter Zoller and his team, which they suggest a very effective replacement for tomography to approximate the second order Rene entropy. If you do enough rotations of the qubits and record the bit strings, and you look at the correlation in the recorded bit strings, you would not construct the full density matrix, but you can approximate the purity, or you can approximate the rate of rho squared from it. And that provides sufficient saving that we could measure the entanglement entropy of this subset of qubits. And you can see we are start deviating from the desired value. This should have peaked about 5, but you can see it comes in 2 segments and they are not exactly at 5. So it's just the coherence in our system leads to excessive entanglement. But after you have done all your subsets and whatnot, you can put them together according to the top formula, and you can arrive at the topological entanglement entropy of the system, which is an independent of the subsystem you chose. And you can see, as theoretical value predicts, you would end up at -1. That's the number you have to get if you have done your work correctly. So this is the first time that we could very directly measure this entanglement entropy of subsystems in our case. Okay, these meant to be logical qubits. That's the essential idea behind them. These topological properties is what led to surface code, and all these codes are in essence topological in nature. So here we can brute force test this idea in a sense that we do not have active error correction, but we can pretend that we can make a logical qubit out of them, and we can call it subset of 3 by 3 or 5 by 5 of them a logical qubit, and we can see that how well it stands and how well behave if we just use it as a logical qubit. The sequence I showed you can be a little modified. So instead of arriving at the, well, okay, so first thing first. I changed the boundary a little bit. So now we have degenerate ground state. Everything I was showing you so far was because of the boundary, the shape of the boundary we chose, and these little things become very important. This had a single ground state. The ground state was not degenerate. But we changed, making minor changes to the boundary. Now we have degenerate ground state. So we can use them as logical qubits. And here we are doing for 3 by 3 and 5 by 5. So by modifying the sequence I showed you a little, you can essentially make states that are in this logical block sphere. This is the logical block sphere. This is north being in 0, south being in 1, and then you can make all the states, and you can see how well you can do it when you go for these very typical states that people are usually interested in making. Try to go to equator, and since this the coherent going to shrink and goes toward the center. But also in doing so, we took advantage of the fact that that essentially we have data qubits and the measure qubit in we can interpret that way. And anytime that you see that your raw data, some of the stabilizers are not showing the value you like, you write a simple algorithm that post-process that data and flip enough number of qubits to restore the shape that you know it is. This is what error correction meant to do actively, but we are just doing it in the post-processing of the data to show what could have happened or how well could have been if we actively correct, although we are just doing it very passively and post-processing at the moment. We're just trying to see what's happening in here as you make the system bigger and bigger. Here I'm showing equivalent of rabbi and ramsay experiment. Essentially, you put the qubit on North Pole and or on 1, logical 1, and or on equator, and you see how long it takes to decay. So it's a little crowded. Let me just walk you through the top panels. What's happening in here? Let's start with these red points. So you make a logical 1, and you look at it, and you know, it's get worse and worse as time goes. So you just leave it there, and 1 means that all these qubits reach state of 1. You do this correction that I mentioned, and you can see your logical 1 can get better. There is some offset coming from at time 0, even without any decoherence, mainly coming from systematic errors and readouts and whatnot, but it gets worse and worse. And even the algorithm cannot correct everything for you and give you a beautiful result, right? It's just to some extent correct it, but then if there's too much error, it's just going to grow on top of each other.
Sorry, Pedram, a question. I guess as a function of time, you do expect this to get worse, right? I guess what is the expectation? Should it be like
the expectation that it's going to go worse, but if the errors are dilute enough, this correction would find them. You see, look at my algorithm. The errors are so frequent that there is no unique. If the errors are dilute, you can really figure out who made the mistake. But if the errors are not dilute, then there are more than one way of correcting it. So you're not really correcting correctly. So the promise is that in the dilute limit, the error is probably much better than this. The corrected would be dead constant and fully taken care of. But I'm trying to say is that the chance of getting errors is still too frequent for all those beautiful theories to kick in and work in.
Does it also depend on the size of the plaquette?
Well, we're going to look at 5.
Oh, okay.
Yeah, right. So you put the qubit on equator, and that's qubits are more sensitive. This is the logical equator now, plus state. And we correct it in 2 steps. One is we apply our algorithm. It does something. It makes it slightly better. But much bigger correction comes from spin echo corrections, right? These qubits were idling on equator, and the T2 decoherence is not very good, much worse than T1. And you really need to be sure qubits are not idling, and introduce something that probably you would call it Hahn spin echo. And if you do that, again, you get to see the best you can get. And that is for 3x3 sets. So, right, as Jawad asking, okay, is there free lunch if you go to 5x5 and magically everything heal itself? The answer is no. The answer is no. Things, the same trends is appearing. It's some loving eye, you might say this is better, but let's not do that. It's not fair. It's one experiment. But the same concept you see here. Maybe the take-home message is that our errors are so close to the threshold that these theories are working. That just having active error correction would not be sufficient, and the error rates and whatnot have to come further down to get these ideas to work. I think maybe that's a fair take-home message in here. It's close to the border. It's not decisively on one side of the border. Okay, and that's the other work we did. This is in collaboration with Stanford and Max Planck, and Shivaji at the time was at Princeton and now currently at Oxford. And on the left, you see people who are made major contributions to this work. And I think it appeared in Nature, eventually appeared in Nature actually last night. This is after preprints and advanced publication and whatnot. Last night eventually got done. But what is the story of time crystal? I think there is something, in fact, putting all the hype aside, there is something actually quite charming and quite interesting about it. Very, very deep and very interesting. See, we are very familiar with the concept of crystals, the spatial ordering, and you can think about them and you can come with lots of examples very quickly. You can have repetition of pattern in space, in ferromagnets, in liquid crystals, in all sorts of other crystals that we are familiar with, rocks and whatnot. And then you say, well, what if I have repetition of pattern in time? And you start thinking about patterns and systems that repeat themselves. It's not hard to come up with systems. You know, a child on a swing, a parametric amplifier, solar system, watch, all of them are repeating in time. But then you realize that there are far fewer degrees of freedom. And then you think harder and harder, you realize it's not very easy to come up with a system that have many degrees of freedom and repeat itself in time. And this is for good reason. This is not impossible to come up with, but the examples are very very few, or maybe close to zero in a sense. So what I'm saying is that you have a crystal, you perturb it somehow with temperature or local probe, and you give it some time, it heals itself. The perturbation is gone and it comes back to its configuration is stable. But imagine you have lots of pendulum that are interacting with each other and they are showing a very nice pattern of oscillation. If you come back and look at them some later instance of time, either their pattern has gone disordered, or if it's ordered is because somehow you're removing the excessive entropy from the system. And it's very hard to imagine that the system repeats itself without generating excessive entropy. But it's not impossible. The second law says entropy cannot decrease, it can increase, or it can remain the same in a closed system. But in reality, remaining the same in a closed system of interacting particles is extremely hard, but not impossible. Since it's not impossible, we elevate that to a definition, very succinct definition for time crystals is indefinite oscillation in a many-body isolated system. And we say, okay, can we go and find them? And it just happened that the example that we know is just in quantum system, and there is no example known in the classical domain that we all agree upon. And this example is stable because of the physics of many-body localization. So if you do not believe many-body localized systems are stable, if you do not think that many-body system is stable and can exist in even in 1D, you don't need to listen to the rest of the talk. But if you think many-body systems are stable, you believe the proof by Imre and the works of Hughes and Altshuler and Aligner and others, then maybe you can continue listening. So this definition I wrote is very succinct: indefinite oscillation in a many-body isolated system. And the work that we wrote is to dissect this definition in few parts and then to provide evidence for each part of it. I wrote a longer definition at the bottom, which is essentially what leads to the 4 figures of the paper, and try to provide evidence. And note that all of them have to be come together to have a time crystal, otherwise would be cheating. It's not what we are after. I think if you drop any of the criteria, any of these 4 criteria, you can quickly find lots of examples and you lose the whole novelty. So it all have to come together. So we're trying to prove it's a phase of matter. So we have to go through a range of parameters and to show that it's stable and is not just a fine-tuned case. It's just a basic requirement for phase. And the hardest criteria is the open and closeness criteria, because we don't have fully closed systems. So we have to argue how close is our system and distinguish internal dynamic from the coherence dynamic. And as I said, many-body localization is the core of the physics, is the essence of the physics. And one of the properties of many-body states or many-body systems that are, I don't want to use the word phase, or in the many-body configuration maybe, is that all the eigenstates are have the same, all the eigenstates are localized, many-body localized. So no matter where you start, you have to, you should see the same physics, and that's just, we put some energy to show that. And thermodynamics phase means that when you take the system size to infinity, you still have the good signal, and the signal doesn't disappear when the system size get larger. So and that's something we would do with finite size scaling. So let's get to it. The system which we believe can show many-body localization is transverse field Ising model, which here we are using the kicked version of it. In a cycle, we have 3 layers of gate, starting with single qubit rotations. X of g means rotate every qubit with an angle g. When g is 1, you go from North Pole to South Pole. And then we have a layer of disorder coupling entangling gate. And then we have the disorder, something which translate into disorder landscape. And so here is the terms of the Hamiltonian, where we're trying to do kicked version of it. We're not trying to realize the Hamiltonian. These are, is e to these 3 summations, is not e to the sum of them, but that's what we intended. But one thing I want to make it clear is the disorder in coupling is very important. These coupling terms have to be non-uniform. And if they are, you would have a very hard time to achieve many-body localization. Here is a hand-wavy argument. Let's say you rotate the qubits with x to the power of g, and let's just, for the sake of argument, drop these entangling gates. They're uniform. And then you see a disorder landscape. You rotate them again, and let's consider the case that g is very close to 1. Now, in the eyes of these qubits, the whole landscape is now flipped. So in 2 cycles, what these qubits see is the landscape and its inverse of it. So effectively, they cancel. Achieving many-body localization in this limit is very hard. So the claim is that if you do not have disorder in Ising, you do not have many-body localization. If you do not have many-body localization, there is no way to have a stable time crystal. So in a different context, it was said about Elvis Presley by John Lennon, but it's the same thing in my mind. If you don't have one, you really don't have, and there was nothing before you can establish this. Okay, so let's forget about entangling and whatnot. I want to show you something super boring. You just rotate the qubits and you see what you see. We see where the z projection of the qubits. This is 20 independent qubits moving independent from each other. There is no entangling gate. And you can see that when you measure the z projection, you get up, down, and you Fourier transform, and you get single peak. That's great. That's when g equals to 1. And then you start turning g from 1 to, let's say, 0.97. You do not complete going from north to south completely. So you see a beating pattern. This is single qubit experiments, essentially. Is nothing fancy about it. And you Fourier transform, you see 2 peaks. That's great. You make G even less perfect, and you see 2 peaks that are splitting from each other. It says that it takes more time to complete your cycle because you're taking imperfect rotations. But something slightly interesting happens when you turn on the coupling, and still you keep G's to be distinct from 1. You see the coupling between them introduce some phase locking that, irrespective of the fact that G is imperfect, they all respond together at the given with the as if G was 1. So there is some phase locking is happening in here. Let me show you schematically. You start with the configuration of qubits, some up down, and then they rotate and they come back to the same configuration. So in the cycle 1, 3, 5, 7, they are showing the same configuration, and the cycle 2, 4, 8, 6, 8, they are showing this different configuration, but they repeat itself. So there is some collective behavior that's really excited the early experimentalists who are working on this subject 5 years ago, and they amplify this concept in their work. But this should not be taken as the sufficient signature of time crystals, because there's nothing quantum in here. It's just a standard phase locking. Human beings at the end of the concerts, they know how to synchronize and clap together. Fireflies know how to do that. This is nothing to do with quantum. It's phase locking, but nothing novel about it to elevate it to a new physics or anything. There is no quantum in here, or is not limited to the domain of quantum. And this is what you see in the early experiments. They are saying that G is imperfect, but then introducing of the interaction between the terms allows you to heal this splitting of the frequencies, and you get back single frequency in spite of having imperfect drive. But as I mentioned, there are several components have to come together to really establish that we have time crystals. And here is the hardest one, and that is separating the internal dynamics from the undesired effects of being coupled to the environment. The way to measure its individual contribution of these two terms is to advance the gates, apply the gates, the system evolves, and then they evolve the system fully backward. Nominally, if everything was perfect, it would have come back and everything, you get 1 all the time. You have constituted a major identity by these two actions. Realistically, in the experiment, is not coming back, and we attribute that to coupling to the environment, the part that cannot be recovered, non-unitary aspect of the dynamics. And that is the black data points that you see on top of the measurements we have done. Essentially, we are doing echo and to see how much is loss is down to echo. And what we could do is the simplest thing that a grad student would think about, and we in fact did that, but the physics actually is backed up by deep physics, that is just simple division of the blue line by the black line is sufficient to remove the effect of decoherence. And after you do the division, you get the lower panels. So when G is close to 1, you see the oscillation that we claim goes indefinitely, or it's our best evidence for going indefinite oscillation. And on the left, you see that when G is substantially away from 1, there's no way to recover it. Even after the division, really the internal thermalization and dynamics of the system is such that you don't have a stable edge states. The middle rows of panels are the space resolved data, and it's boring because all the qubits are doing the same thing in synchrony. But to disclose the whole thing, we are showing it so you can see 20 qubits are doing same behavior. So this is all the physics of many-body localization. And this is our simplified version of out-of-order time correlation measurement, or you can call it providing evidence for the absence of diffusion. If the system is localized and you have a local perturbation, it should not diffuse to its surrounding qubits. So we consider two initial states. One is all qubits 0, another is all qubits 0 except qubit 11 being excited. And we measure Z projection on that qubit. Clearly, that qubit is seeing the difference of the initial states. But as you go further down the chain, when you arrive at qubit 14, the qubit 14 could not care less if the initial state at qubit 11 what it was, and that is the essence of localization, that the perturbations remain local. The diffusion of the particles would not happen. However, if you're not careful with the choice of the entangling gates, they are not uniform. Sorry, they are uniform, they are single valued. Then you would see that qubit 14 is quite sensible to what's happening upstream at qubit 11. And so their system is not really uniform, localized. And to simplify this curve in a single number, we came up with something that I think is called zeta subtraction divided by summation. So it's just a single number to represent these curves. And you can see here we are showing that zeta R, probably average over disorder realizations. And you can see in the what we claim is the localized case, this excitation or this zeta does not show any propagation. However, in the case that we are saying is not many-body localized, you can see that it's fanning out, and that's exactly what you probably expect for diffusion. And here I'm showing line cuts. And to the expert in the audience, we are saying that it seems there's a phase transition below certain values. The eigenstates are not all many-body localized, but don't worry about that detail. Okay, so let me provide the last bits of evidence, maybe in last 3 minutes, and then we take it from there. We want to show that for all initial states, this physics hold. So we here start with 3 distinct initial states that everyone could think about. Nil being 1, 0, 1, 0, polarized means all 0 or all 1, and random means a combination of zeros and ones. And again, we see that the response of the system is not depend on the choice of initial states. So for all initial states, that the system is doing the same thing. However, the response substantially varies when you are not in the many-body localized phase. And you can choose 500 different initial states, and I'm showing you the histogram of the response. I don't know, maybe a cycle 30 or something. And you see that there is a very tight distribution. Sigma over mu is 4 times smaller than the case that is not many-body localized. And all these states, in fact, were showing the typical behavior of it, while in this case, they are not showing the typical behavior. So it's Very important that you establish localization and you have couplings to be non-uniform. Okay, this is a bit involved slide, but I hopefully can walk you through it. 500 initial states I just mentioned is really a fraction of the Hilbert space. Hilbert space in this case was 1 million dimensions. So you have to really do something better. And the idea, as it was reminded by us, by our experimental guru and our role model, is that we can use typicality. Typicality is that you have one state which represent the typical, which can help you to see the typical behavior of the entire spectrum. That state has to be fully Haar random, fully uniformly exploring the available Hilbert space. So when we start with our bit strings, we put a scrambling circuit, which we scramble that state. It is fully Haar random, is not fully bit string random. So you have to randomize your random bit strings to make it fully Haar random. That's scrambled psi. And then you have to start with that initial state rather than the product states. The complication happens is that now you have to read ZTZ of 0, these 2-point correlation functions, but you cannot do that easily for arbitrary states. So far we could do it because states were product states, initial states. But then entangling it with an ancillary qubit allows you to measure exactly what you want from the ancilla qubit. So there are two additions. One is this scrambling circuit, which depending on the depth of it, you start from product state, you scramble better and better. And then the complication of reading these 2-point correlation function, which we solve by adding an ancillary qubit. So that's the new setup we have to use in here. And the data looks more or less the same as we used to do, but now the claim is that this is the typical behavior of the entire spectra, because we are appealing to this typicality condition, to typicality assumption. Again, there is a decaying signal, there is normalization, there's echoing, you divide them, and you see a rather stable signal. And you can do it for different depths and different values of scrambling, different choices of initial state. And you can see indeed it gets sharper and sharper. So there is a typical behavior of the spectrum can be really pulled out when you have a really good Haar state. K20 means 20 layered of scrambled states. Okay. So let me finish and then I take questions. As I promised, we're going to do finite sizes scaling. The order parameter for this that we borrowed is from the spin glass literature, and it's called the Edward Anderson order parameter. And all we mean in here, we don't mean any glassy behavior or anything. All we mean is that do the long range correlations survive as you make the system bigger and bigger? Well, 20 qubits was enough a stretch for us, so we didn't make the system bigger and bigger. We made it smaller and smaller. So we had to start cutting qubits at the end of it. And we look at this Edward Anderson order parameter as a function of control parameter being G values. So you see above certain threshold crossing value, as you go the system bigger and bigger from 8 to 20, this order parameter gets better and better. Below the crossing point, it gets weaker and weaker. So meaning that if you had gone to infinite size system, God's willing, and you're above the crossing point, the order parameter would survive. So that's the last bits of evidence for this. I'm out of time to go to this experiment, but maybe I put a conclusion and I take your questions. The conclusion is that we are taking smaller steps toward doing something, some physics problems, some chemistry problems that is beyond the capability of classical computers and have a large community of interest. And all these experiments are pieces that are coming together in this regard.
Okay, thank you, Pedram. Thank you for a great talk. So I will open the session for questions if anybody is interested about I guess the work, the topic. So I guess, I can ask a very quick question. So this is the same CPU, I guess you call it Sycamore.
Yes.
And then there's the variational.
Well, I think we have a couple of them, but nominally are the same. When people work in the lab, they could log into several of the processors. Some data is coming from this chip that it just goes.
So basically, if it's like a 50 qubit, you can always, for this, for example, time crystal, you want the best 20, which are configurable and they're kind of close together. So you can sort of pick by this configurability. Okay, awesome.
Yeah, it's always the option.
Okay, any question? I would have imagined there was a lot of complaints about time crystal. There is always one.
Yeah.
So I guess a fair and academic comparison between Chris Monroe's and Michelle Lukin's experiment and this new one, what would it be? Because they were also talking about 50 qubit long range, right? I don't remember exactly though, but what would be kind of the?
I think Michelle Lukin's work is very humbly say that they see this phase locking, and they were really surprised that interaction-induced phase locking was observed. And it's a 3D case or 2D. So there's no way that you can convince MBL community that is surviving, right? MBL community at best agree that MBL survives in 1D, and 2D no one, and even 1D the disagreement still exists. So there was no notion of indefiniteness in the work of Michelle Lukin. I think the work of Chris Monroe and his team also show some aspects of the work, but our claim is that we are really putting it together, and we are doing ruling out the coherence from internal dynamics. We are really working hard to establish many-body localization. And if you read the manuscript, you see there's always this reference to many-body localization, and these parameters all are shown that are to emphasize that you got to be on the MBL regime, otherwise you would see oscillations which eventually dies out. But if you really want to satisfy theorists in terms of infinite oscillation, it's beyond the capability of any hardware. They're talking about 10,000 cycles, and something is so beyond humanly possible.
Oh, we get there. It's just a matter of time. Any question? So one thing that I guess I can ask another question again between Misha and Chris. So those systems, basically, when they were operating, they were already outside their T1, T2, if I remember. So in yours, are you still within that coherence time?
As much as it's, I think
is it fully quantum, or is it not fully quantum, I guess?
No, it's very well within the range. Is close to the T1 of let me see, 100. Yeah, it is well within the range still. You cannot really go beyond. Is as much as you can go with this division, right? Or as you can see, so you have to divide these two things to get the unitary out of the. You get to divide the blue by black, and then you divide two numbers which are getting very close to zero, and to build substantial that maybe the other case is more visible.
Yeah, I see. Okay.
So this is the challenge. To overcome the 1 over square root of n noise of this, you have to really average for a long time. So technically you can keep going and to pull out the two dynamics, but
okay.
I think we do have maybe 150 cycles now, but is if someone is a non-believer, it's going to stay non-believer.
Yeah, a factor of 2, I guess. Yeah, it's not.
They're not going to. Yeah.
Sounds good. Any question, I guess, from the audience? I guess if you have no question, we virtually thank you.
Sure, sure.
Thank you for the great talk and kind of bringing us up to date to latest Google experiments, and hopefully we see each other soon.
Yes, yes. Thanks. Sure.
Yeah. Thanks, Pedram, and graduate students who are graduating, contact Pedram.
Yeah, definitely, yes. Yes, yes.
Right. Okay, thank you so much.
Thanks. Yeah.
Thank you.
Thank you.
Thanks, Pedram.
Sure, sure.